It's a great pleasure to introduce you and welcome here Boleslaw for the friends. Yes. Szymanski. And now I can go on for probably half an hour about the wonderful things he did, and just to tell you, 300 more scientific articles, a member of the National Academy of Science in Poland, triple IE fellow, national lecturer for the ACM, and so for who is not in the computer science, since this is a very interdisciplinary institute, these are major award in computer science. He got the Wilkes Medal from the British Computer Society and the widely distinguished faculty award from the Rensselaer Polytechnic Institute, where he is now. And he's one of the big guy in network science, because a few years ago he started this big initiative for the entire community. So he became the reference point for the Army Research Lab in what is the exact name is Social and Cognitive Networks Academic Research Center. And so basically this is where a lot of the nice and interesting studies about social networks, cognitive networks, and many other things have happened in the last years. He has coordinated a very large number of network scientists for many years, and so it's aside all that work, and honestly also finds time still to do a lot of active research. And so he will tell us today about failures, dynamics, evolution, and control of the global risk network. That's a very interesting talk. Thank you very much, Oleg. Please,
thank you.
The floor is yours.
So let me briefly tell you that this is the collective work with students, postdocs, and two professors, Jack Sigao, who joined us recently, and my good friend and colleague George Cornish from physics. And it's done in the NEST Center, which unites people from different disciplines in the world. It was inspired by my visit to World Economic Forum in 2013, and I noticed that they do there a very interesting study of global risk network. And I would talk about this study, providing first background information, go through the model details and dynamics, then would discuss limits of parameter recovery, and then evolution patterns of the World Economic Forum over years. Finally, we would talk something which, of course, is influenced by Jiangxi, control of the global risk networks, and with some conclusion. So, as I mentioned, I was intrigued, because then, World Economic Forum put enormous work to gather and define global risks and provide the structure and view. And it was that. It was that in the sense that it's like picture of the city in which you take the view of all the buildings but don't see people. It doesn't tell you much about what's going on in this city. So then what we did, we provided some parameters and asked, it's not a snapshot, it's a live movie. It's a system which evolves, and how we can find what evolves, what changes, and how it is dynamically changing. So global risks are defined by World Economic Forum each year because different things would happen at different years, would be like on the agenda of discussion, how to abet them and what to do about them. And each year, this report identifies 30 to 50 global risks which are either active or are likely to be active, and they are classified in 5 broad categories. Some of them very quantitative, like economic, technological, environmental. With the bracket, hurricane strikes, you know what the damage was. It's measurable. But also less quantifying, like societal and geopolitical. And also it provides 3 dimensions of assessment of these risks. First is impact, very important for economists. The other is interconnectedness, how they are connected and interact with each other. And the third is likelihood materialization in the next 10 years. And that is it. So while it's really static, provides every year new picture which changes from year to year, but nothing about what's going in between, what drives it, and so forth. So then we, for example, have a newest report published like a few days ago on January 18, and in which we see that there are 30 global risks, and what the report provides is this two-dimensional view, for example, likelihood versus impact, when we see how different risks are classified. And of course, the most important are the risks in this corner, because those are the risks which are first very likely to happen, and also very impactful, because they provide a high cost when they are realized. Of course, there is also some view looking into how they are interconnected. So the interconnection between them shows which risk influences each other. And we found out very interestingly, which surprised us, that dynamic analysis of the past versus the risk network showed that the influence is mutual, and the influence does not depend on what risk they are. It depends only on the connectiveness of the and likelihood of the risk, which is the source of the influence. So the risk, as I mentioned, come into these 5 groups, like societal, shown here, some protests, here is environmental, tsunami creating the fire, natural disaster in terms of drought, of course, weapons of mass destruction as an example of technology, which can go wrong, and also cyber attacks. So those are the vivid examples. And then, from that, we want to do the dynamics. So of course, we can see it as sort of either as I model, when we have 2 states, suspected and, susceptible and infected. We can look also from the point of view of control theory, when you would see, for example, either operating on failure. So in our case, actually, we have the states of active or non-active. So that when the risk is only non-active, it's susceptible to become active. And of course, active state is a bad state in which we have consequences. So then, as I mentioned, we know likelihood of failure in the next 10 days, and failure impact, and also each was assessed by 20 to 25 experts. We then found out that because of the grouping into these 5 categories, in fact, it's a stochastic block model graph in which the groups are more clustered together than the rest of it, quite well connected with 20.6 connections, and the optimal model can measure how decreasing the strength of each of the risks impact the critical nodes and edges. And therefore, very important it is to understand whether it's better to impact nodes or edges, for example, and the answer is it's much better to impact the nodes, internal risk of likelihood, than just connections. And then the goal is to have the system into 0 failures active, because then everything goes well. So here is this stochastic block model in which we show that node's color indicates total connectivity, because we see only partial connectivity outside of each group. Node size indicates internal likelihood of activation, and as the result, if we think about it, of course, nodes which are large, like 17 or 8, are the most dangerous because they provide a very high likelihood of materialization, activation, and of course, when node 8 is stronger because it's darker and therefore has higher contagion capability. The number of links shows strength of connectivity between the pairs of groups, and of course the probability is provided. As we see, 40 is 46 are the highest, 52 is the highest at the top, and some of them are not well connected because probability of connection here, for example, is only 24%. So the model, because we look at the reliability theory in engineering, could be called alternative renewal process, because in the theory of control, engineers tell about the renewal of the machine which failed by the process of repair. And therefore, there is this model alternating renewal process in which the processes are Poisson processes, and theory is well understood and limited just to binary states and the uniform Poisson probabilities. So we extended this model in order to fit our needs. Now we can have more than just two states. We also can have, for example, the state of failure, but also then recovery, and then only the state of being susceptible again. Here we, in the first model, which I'm discussing here, later I will discuss the other, we have just two. One is materialized or active, the other is not materialized or inactive. And transition is really free processes. And what is important that these free processes split into processes which are observable, like recovery. So when recovery always comes only for the risks from internal reasons. On the other hand, materialization could be done either through the process which is internal or through the process number 3, which is external, impact of the other risk. And then they are latent because we don't know what was the real cause. We only observe that the state of the risk changed. We don't know what was the cause, whether it was internal or external. And this is an important contribution here, that we are able to find out the split of these probabilities between external and internal based on the past data. So the model dynamics is Markovian, and it progresses in time step. Time step is equal to 1 month, which is carefully chosen in order to account for quantitative and qualitative, risks. Like, for example, at what time, for example, high inflation appeared. It's not like one point in time, it's maybe the period. On the other hand, the time when the hurricane struck the land is very well measured, the day or even hour. So clearly then it's a balance between the needs of different cases. We also showed that it doesn't matter, because whether we use this process, Poisson process, or we use Bernoulli corresponding process, the outside result, if everything done is the same tick, would be the same. And that's simple proof. So we have this process in which risk I is inactive at time t1, has some probability pi in t, which elementary is just from the Poisson process defined by the simple equations. So we have these two latent processes of materialization and one observable process of recovery. And we can draw a very nice graph of how the change of state happens. And in case of, active risk, the active risk can influence transfer into active risk of the neighbor. So that's a case of influence. So as you see, diagram is not too complex. Now, very important that now we are creating a team from experts which provide these assessments and machine which provide the dynamics of the system. And the question arises, to what extent we can find out whether or not this is a good assessment. Because there is a big dispute between psychologists whether or not humans can predict probabilities of rare events. And there is a big healthy skepticism how it is done. However, what works for us, that the World Economic Forum did a very good job gathering experts. Namely, they select experts from 3 different backgrounds: government, then industry, and then academics, from very wide spectrum of experts all over the world, many cultures, many countries, and also even across the gender and age and everything. So diversity helps, because then crowdsourcing should provide reasonable results. But to account for that, we first take the scale of this likelihood, which was from between 1 to 5, and map it into the probability or likelihood in the measure of probability. But then we say, for reasons that we don't know whether there is inflation or deflation of the probability in different ranges, we allow coefficients alpha, beta, gamma to shape the curve of real probability as a function of this normalized likelihood. And we do that in order to see how good the measurements are in confronted with the past data. So to parameter recovery formulation then could be defined that intensity of these processes are dependent on alpha, beta, gamma and logarithm of either 1 minus the normalized likelihood or just logarithm of likelihood. And then from that we use maximum likelihood estimation, MLE, because we take into account the observed sequence S1 to ST. And then we take logarithm of likelihood that it materializes in the given system if we have R risk and T, capital T time ticks with the data from the past. So then we then see that this likelihood could be defined by the probability that this PI is of this value for this transition. So as the result, the optimal value, which provides the highest likelihood for this sequence, would be the value which we believe is the true values of these parameters. And what is very interesting, that we found out that mathematically it's a very nice formulation because the function is very smooth around the optimum. Here the snapshot of the maximum of likelihood as a slices is a three-dimensional curve. So we represent it through the slices in 2 dimensions, beta alpha with the set gamma, gamma alpha with the set beta, and also the beta gamma with the set alpha. As you see, all are very smooth around the optimum, and the optimum point is relatively flat. So therefore, any errors coming from imperfection of data would have minimal impact on the value of parameters. So that enables us to do a very, very fast search by using logarithm step. We first find out the first cube with the optimum value, and then divide this cube into 8 cubes, in which we find out another cube, which is the maximum value, and so forth. Very quickly, we can get digits of the solution. What is amazing, that these values show that the prediction of the expert is very close to reality. If we substitute alpha, beta, and connectivity, we get that the value of the exponent is very close to 1. So in other words, probabilities are becoming almost equal to the estimated normalized likelihood. And the error is like 3–4% for each. So indeed, the crowdsourcing worked very, very well here. Now, of course, big question was, how did they get these 7,800 points in time to decide which risk was active or not? Here, a bit of magic from computer science came to view. What we did collection of the data from known sources, starting with classification through Wikipedia, and then going to the sources like serious journals, and then weeklies, and so forth, and screening for the terms which describe each global risk. Each global risk is defined by global risk group in terms of keywords. So we find all the publications about the keywords, and then from these publications we get the dates when they describe an occurrence of this risk, and then we screen this 20,000 through painstaking work, looking over and seeing whether they classify or not. About 30% of them classified as relevant and provide us with the values when each particular crisis was present, like in Syria, Libya, for example, and so forth. And the classification is a global and serious, That's 30%, the others are either non-global or not serious, and therefore were rejected. Anyway, that way we were able to find alpha, beta, gamma, and from that we are also able to find out but they change over the years. For example, if you compare 2013 to 2017, the graphs are different, number of nodes is different, but average degree, as you see, seemingly 2017 has lower average degree, but it's better connected because it has fewer nodes. So in other words, probability of hitting the edge is above 50%, when in 2017 it was below. So as the result, as you see, remember alpha and beta tell us what is the impact of direct versus indirect risk activation, and we see that both values are higher for the 2017 they were in 2013. But recovery is, as you see, faster, so therefore overall risks are less active. Now, the second part of the figure, which I showed as a stochastic block model, is the figure showing contagion potentials versus internal vulnerability of the nodes. That's very important because we may have a very difficult to trigger risk, which will be increasingly very contagious, and therefore very ignition would infect many. Or we can have situation in which very easily flaring risk is not so well connected, so therefore it's sort of almost irrelevant. So here in this plot we show all 5 groups and show, for example, an interesting nodes. That's the matrix from the 2013. As you see, the number 8, which I mentioned earlier, is very contagious and very likely, so therefore it's one of the most important. And this is severe income disparity. As you might remember, 2013 was the year in which we still have this financial problem in the whole world related to the housing markets collapsing in many countries. That created a lot of resentment and happiness, and also created that, you know, many people from middle class losing houses, so they were moving to the lower class. So income disparity, Gini index, as economists call it, increased in many countries very much at that time. Then another one was rising greenhouse emission, but now that this was not so impactful because the connectivity was low, so contagion was low. But global government failure was important, and in fact, this was this problem because global government failure means that the people breaking the rules are not punished. A good example of that was, for example, Syria using poison gases on the population, and because of some countries prevent sanctions from the United Nations, this was like encouraging bad behavior. And as the result, as you all know, in 2016, migration problem increased enormously in Europe, which created another flare of the risk, which you would see when you look at the evolution. Now, also, as you see here, we show that the persistence is also a very important feature, and this persistence varies widely within the groups. And some of the leaders is chronic fiscal imbalances, severe income disparity, and so forth, and so water supply, rising greenhouses. So in there, it's really important to see risk persistence, which is not visible in the measurements in the World Economic Forum. It is revealed only when you have equations describing the dynamics of the system, and we run these equations to the steady state, which show us what would be the state of the world a few years later if nothing would be done. And that is the measure which tells us what we avoided by collective actions of the government, international organization, and industry. So the conclusion for 2013 data, we rank order the persistent various risk during the lifetime of Cascade, and strikingly severe income disparity was active about 80% of the lifetime of the Cascade on average. While in comparison, second most persistent active risk, chronic fiscal imbalances, was active only 1/3 of the time. So big difference. When we publish it, then later people confirm that, Berkeley and others said yes, severe income disparity was very important. decreasing the internal failure and external influence probability of global risk both contribute to stability of global economy. But the reduction of internal failure is much more effective. So the root cause, the internal probability, is more important than, at this state of the economy, more important than interconnectivity. Now, the other question which was brought by this research, which we tackled in another paper, the previous was based on the paper from 2015, is the more recent 2017 paper in which we ask how much data help. So what is the effect of having more and more data? Can we really increase our prediction? So in the global risk network, we recover hidden and explicit parameters of the model and then try to predict the future using this model. And how reliable it is and how the recovery precision depends on the complexity of the model was the question which we tried to answer. So for that, we did something different. Because for this, we needed to know the future. And when the modeler is omnipotent, when he works on the model, he invented himself or herself. Because then we know everything about that, what to predict. So we created a model of fire propagation through artificial city, in which we have modular blocks could be assembled into small city, big city, whatever we want, with predefined properties of varying size, varying periods of time, and use the maximum likelihood estimation to recover parameters and compare them with reality. So model details are as follows. This is our repeatable block, in which we have half part of the city consisting of the large plots, large houses built from excellent material, and as the result, well resistant to the fire. And as you see, the circle of fire carrying touches only 2 neighbors, or maybe like 5 neighbors, or 3 or 2, depending where we are. Like for this guy, only 2 neighbors would be affected. For this guy, it would be 3. So that is really a very good place to live. Now we have more dense housing, still decent material, still decent lot size, but the number of neighbors increases. And finally, we have crowded when their houses are more shabby and the lots are smaller, and the ring of fire now encompasses a lot of houses. So this house on fire can potentially create a cause of fire for others. Then what we did, we created a model in which dynamics was very similar. We will have susceptible house can catch fire, then when it catches internally and externally, so we have again latent variables. House on fire can recover by fire engine coming and extinguishing the fire, and then there is rebuilding. And we assume again, to be, representing reality, that big houses have people who have resources, so therefore they rebuild quickly, and small houses are people who don't have resources, so they rebuild much longer. So that way we create a very diverse neighborhood, and then we can study. First we see that the selection of the time peak is not important. We compared model which is discrete versus ODE, which is continuous time, and the results are minimally different, and the steady state is minimally different. And the same story is when we look, for example, we compare here boundaries model of the city, torus, so everybody is neighbor of everybody else, versus looking at the model in which we are fully connected, but square. So therefore, there's edges of the city. As the result, we see the dynamics is very similar whether we look for the susceptible houses, on fire houses, or recovery houses in these two models. So therefore, we know that those are equivalent. Second, when we look at the degree of each house, the houses which are similar are the same color. And more intensive color, more dangerous house. Because yes, these are crowded houses here, but they have fewer neighbors than the houses in the middle. And then we found out that the luck plays a role. Look at these two houses. this and this, we are next to each other in very bad place, a lot of neighbors, and one of them is green, the other is dark. So luck plays a role. Longer we run, there will be the variance between the fires despite similar conditions. But still the rule is here, the most dark blue are in the corners or near the corners, and really the place is important, how likely you are to catch the fire. And then we look at how to measure performance of estimated parameters. And here is a bit tricky assumption. So we don't know in what world we live, how unexceptional our world is. All physicists assume we are unexceptional. We are just like, with the middle of the normal distribution. So we did the same. So how we did it? We take 125 sets of time series, which is simulated for 6,400 steps, using some assumed parameters alpha, beta, gamma, delta, and then using maximum likelihood to recover 125 different values of sets of parameters. And then, using estimated parameters, we simulate multiple length of future periods for some time series, and record length of normal, on-fire, and recovery state, as well as number of emerging fires over 20 realizations. So we have now, for these 125 sets of parameters, we have now corresponding future of the cities with these parameters. Finally, we measure the distance between estimated parameters and ground truth parameters, which are those, in terms of Kolmogorov-Smirnov metric, and then reject all the sets which are more than 1 sigma away from the true value. That says that if we are normal, then whatever version of the world we run, this version would be within 1 sigma from the true value. And therefore that we get these 39 sets of results, and the remaining results which are rejected, then this contains 68% of all sets of estimated parameter values. So that means that we expect our world to be normal. From that, we can find out what is the value of ground truth parameters, and those are blue. What is the value of average of estimated parameters? Not surprisingly, we have the same ground truth. So because we are within the 1 sigma, if we sum them up, we should get the average value. And what is the boundary? So in other words, what are the worst parameters and best parameters away from 1 sigma from the values? And we see that the error is relatively small. And this error is encouraging because it tells us that we are very close to the ground truth. You see, even here we have about maybe the length differing by 1 point, and here we are having the length varying also about 1 point. What is also surprising, that maybe distribution of the length is different, but the number of fires is just on target no matter which value we take. So, in other words, the model recovers the outside effects, number of fires, almost perfectly with this assumption. Second question which arises is how much we differ in recovering global risks if we take data from the shorter periods, like 120, which is 10 years, 240, which is 20 years, then 40 years and 80 years. We see that what happens, the error is decreasing very rapidly, and even more, if you look carefully in the log-log scale, we notice that the standard deviation of relative error has a slope minus 0.5, and it decreases according to the power law to 0. That is something which confirms the theoretical result that maximum likelihood evaluation is asymptotically normal, but is the first example in which we have also latent variables. In the presence of latent variables, this result was not known. In fact, we have now confirmation that is very nicely behaving. So more data would bring us more precision. And here's the example. If we have only 10 years, we have very flat normal distribution and far from the average number of materialization. And this distributions become sharper and sharper and closer to the true value when we increase the length. And then, of course, we see also how it decreases very nicely. But again, if we look at number of materialization of each risk with 960, we again see very good results saying that it may differ in the length, it may differ of each stage, but the number of fires will be the same. So again, it's a very, very encouraging result. So now, in a conclusion and future plans for this part, we want to conclude as follows: that simulations of discrete and continuous risk model match each other, which means that where really models are the same. The parameter recovery performance improves and its error decreases when the volume of training data grows. So relative error reduces asymptotically to zero with unlimited growth of training data, no matter how the complex system is, because we try the homogeneous cities, very diverse cities, the results hold. And then, in future plans, we would like to consider more complex model than 3 states. We would like to measure the prediction accuracy using other statistical metrics. And we would like to study application combining human experts assessment with the stochastic computer predictions based on MLE recovered parameters on regional models, like Asia model, or North Africa model, or European Union model, or even US model, South America model. Those models which bring a lot of local issues and neighborhood of neighbors. In other words, countries there are close to each other and have a lot of influence just because of geographical position and shared culture. Now we are interested in understanding global evolution, the most exciting part of the model, when we look into how the risk change over time. So first, we want to understand how the fraction of external and internal global risk activation changes over time. So there's a derivation which shows that we can look at the global variables, like how many internal fires we had, external fires, and so forth. And from these coefficients, we can find out that for cases when the terror approximation could be used, in other words, when the normalized likelihood is low, it's simply just the beta times the number of probabilities of the neighbors divided by alpha. And these values change from 2013 network from 269 to 307. So that shows something understandable, because we increase the connectivity by about 30% percentage of connectivity from 42 to 62. Then we see that really network in 2017 was less stretched than it was 2013, just by comparison of these factors. We also can notice the different behavior in time. So if we compare, for example, average value of the risk in 2013 and 2017, look at the values. A lot of risks in 2017 are very close to the average value, whereas here we have enormous peaks, but also bigger dips. And then if we compare, that was for the case of the first fraction, internal fraction, but if we look at the external fraction, we see very similar pattern. Here now is higher, but average is close to the values, whereas here it was lower, probably somewhere here, but we have a big dips. So variance was much bigger in the 2013 network than the 2017 network. But the overall risk was lower in case of 2017. So as we see, that's again visible in this plot. The other thing which is important is the risk influence, and we notice that 2017 network has the largest distance just 2, which says how well it is connected. That 2 risks are no farther from each other than just 2 steps away. So therefore we try to assess how much the nearest neighbors versus second level neighbors impact the node. And what we found out that it's in unstable transient state, which we get when we look at the network through the eyes of the January report from World Economic Forum, there is almost no impact from the second layer, only impact from the first layer. But as we move into the stable state, this very much changes because the impact of the first layer quickly drops and become very comparable to the internal layer. By internal layer is highest at about 11, still small compared to green, but closer to the steady value we have the proportion, which is closer, like 4 to 1. In the 1,000 step we have 96 versus 27, of course, in promiles. And here is the show how big difference is maximum in one case, and also how quickly it drops. So when we have the maximum over here, we have much closer this ratio to this than we had here, that it was almost 0 versus very high value. What is also interesting when we look at the influence among risks, in 2013 networks it was very broad. Economic was all over 50% influence, where now, as you see in 2017, it never reaches even. The highest is 30%. What happened that environmental was also quite a few times about 50%, 1, 2, 3 cases. And geopolitical was also 4 times over 50. And societal was just once. But here we have only environmental high, because we are in 2 places over 50, and also geopolitical 2. So it's much wider world in 2017 than 2013. So people who despair about what's going on, it's not so bad as it was in 2013, globally. And here is the example. As you see, all 3 risks were 3 groups of risks were influencing over 3 different, other groups versus geopolitical, which is the only one now having 3 risks, 50% or higher, 3 groups of risk, in 2017. 3 to 1 is a big difference. So now, if we look at the issue of control, we want to impose a consistent dynamics, a control which would bring the system back to the desired state. Difficulty here is that unlike the other systems which control was described so far, it is unstable state because it spontaneously changes to the state in which one of the risks is becoming internally ignited and then can externally ignite others. So therefore it's a more tricky how to control it, and the probability of likelihood is very important cost in which has to be included. I will discuss it. But just remember that we have this system dynamics and control. Control is imposed in order to stabilize the system. And we try to linearize it. We see that, in the function we have this Hadamard product, which defines dynamics, and then we just go by linearization of state matrix and input matrix. State matrix would have these, elements from the matrix A. And then, with this, we can now try to find optimal control in general representation when we move from the step k to k plus 1, the function is nonlinear function f, defined both by the step k, by the internal state and the control state. And we of course want to do it using minimal energy, so we want to minimize J, which then, for this condition, means that we would have to have derivatives which are defined over here, 0 of the Hamiltonian, and then, we would have the next step is defined by the derivative of a lambda, and this one has to reduce to lambda k. So with this, now we can find 2000 network control inputs, and as you see, they are very similar between linearized and original nonlinear system, but of course, because of no error of approximation in linearization, the control is smaller. If you look at these lines, you definitely here have more energy on the left than on the right. These curves goes down to larger negative energy needed to quiet down the system. Compare this to this and this to this. And then we see that the evolution of the system for the network of the states. We have the states which initially were 1, we quiet them to 0. Others were flat, so therefore they ignited by this existing 1 state before they got to 0. So as the result, we have the slow change to the state desired in step number 30, number of risks, in which you would have all states in 0. And again, we see that it goes better for the original nonlinear system because, again, the states flare slower than here. If you compare, for example, this to this, you will see slight difference. So now we can translate that into control energy. So please note that the number of drivers nodes is important. So in 2013, it was so bad that we needed at least 10 drivers in order to get finite energy to control. Whereas in 2014, it was just 6, and 2015, just 5, and then we go back to 6 and 6 in 16 and 17. And the level of energy, of course, was smaller and smaller, because if we increase number of drivers, we see that smaller and smaller energy is needed. So larger and larger, darker colors. And optimal control, as you see, minimal energy has the same shape for all years, whether linear or nonlinear. However, the energy by nonlinear is slightly smaller because of this efficiency of not going through approximation. So just to finish, conclusion and future plans. So it is a working stage. We are working on the paper. We are completing the results and preparing the paper. But already we notice very interesting conclusions. The linear approximation works well and allows us to find the solution analytically. The original nonlinear solution serves here as validation and measurement of the precision of linear approximation. The non-negative control requires all risk nodes to be drivers, otherwise we cannot control the system. However, a very important thing is desired state is unstable. In novel cases, control so far was used to bring only system to the attractor, to the stable state. So we need to use control input either continuously to even not allow any risk to arise, or in response to this activation, we need to nudge the system to the desired state. That means that optimal energy has two parts here. Energy exercise in order to control the system, plus energy lost when the risk become active and therefore cause bad effects for the global economy. And that's something which was not addressed so far in the publications. In future plans, we compare control of risk network to control of epidemics and other archetypal systems, like for example, ecosystems, and using optimal control energy as a measure of a system instability. Because in a sense, how much energy is needed to quiet the system down to initial state tells us how bad shape a global economy is. So those are our plans, and hopefully we will be able to do it. Thank you very much.
let me open the floor to questions. I can start with one, Bolen, that actually goes back to the first part of the talk, and I don't know if it's something that we discussed already. So you define basically all the measure of risk on these basically expert supervised assessment of risk that is between 0 and 5.
1 and 5,
1
and
and
we
5.
scale them, normalize them into 1 to
Yeah.
4.
Now, you normalize it to 0, 1 according
Yes.
to a linear scale.
Yes.
But generally, the perception of people when they give you those kind of risk metrics is not very linear in general. So you tend 0 is very small. It's a little bit more like earthquakes, in which you tend to say that this is more orders of magnitude. So if I say 1, this is 1 order of magnitude less than 2, and so on and so forth. So how it is that, yeah.
Yes, so you remember these parameters, alpha, beta, gamma?
Yeah.
They are capable of, really, depending on what value you choose, then you would see that we can get very convex, or, curve, whatever curve you can shape, which, if this effect would be there, the alpha would come out different than it came. So really, what we say is that, in fact, this normalized likelihood, if you measure not the likelihood of internal and external, but cumulative, what you observe. So in other words, they provide likelihood of not internal or external ignition, but they provide probability that this risk would be active. And that includes both internal and external. So this is why we need to take into account intensity of these two processes. Lambda internal, what is the internal probability, and lambda external. The sum of these two provide us with the conclusion that if you substitute alpha and beta in the formulas, we would get exactly, almost linear, it's like 0.99 instead of 1 to the power 1 minus ni. Just to show you what I'm talking about. Yeah. So we don't believe this value. We don't say it's a probability. Probability is 1 minus ni to alpha. So if I set alpha equals 0, I would say, well, no matter what they say, it's like 100%. If I set alpha equal 1, I will get exactly the value which they say. But if I say alpha very, very large, then what would happen? I can really map this on very convex and shape depending on what it is. So the point is that the value of alpha which we have, if substituting these two probabilities and compute, we get 1 minus ni to the power like 0.99 instead of 1. So that corresponds to the error of like 4% on the likelihood. So that's amazing. We are surprised. And we work with John Bagdash, his co-author, his psychologist, whose advisor is a famous guy who worked on this crowdsourcing. So he even reported it to him because that's remarkable, and he explained to us that's possible because we were independent. The experts were independent. It's what we see is average, not the value which any person gave, average of 25 experts.
Excellent talk. Perhaps I missed this somewhere, but I would expect that external risk impacts also internal risk. That I expected to see a lot more conditional probabilities that I saw.
Right, but in a sense we sort of separate them in the formulas mathematically because we assume that, we have to assume priority of one over the other. So in the case we have both indicated that it would happen, only one would be, and we say that internal is more primary.
I see.
So
then in your models you're assuming they're mutually exclusive?
Yes.
Oh wow. Okay.
Oh, yes, and this is why we write that. But that's a very good solution because when you have the situation that you flip the coin, of course, in the simulation. So if both say yes, we say no. It was first internal. First the guys, slept on the couch and put house on fire, and then the neighbors brought the fire into it. So, but that's arbitrary decision, I agree. And you know, if you would resolve it opposite, nothing would change except it would be more external than internal. That we have now more internal than external in reality. The other way would be to taking half, but I debated it, talked to some mathematicians, and say, no, exclusive is good.
I see, okay.
Because you cannot put the house on fire which is on fire. So if you assume the primary is the internal fire, then of course you say, okay, this house on fire, it doesn't matter that wind blow and brought the fire from the other house.
Hello, nice to see you. So I was curious about the control piece. So in the examples that you gave, I can imagine some cases we want to get things down to zero, like weapons of mass destruction, right? I can't think of a good reason why we want those to propagate. But what about social protests? And I think
Yes!
expect this
A
question.
perfect example. So
what
I
if we wanted
can
to not
immediately
do
explain to you why I have this dilemma.
Yeah.
So suppose that we consider the situation of social arrest or unrest.
Right.
So solution which was really implemented in East Germany under communist time, but they assume that to have, you know, any group, you needed at least 4 people. So what they did, they recruit 1/4 of the population as Stasi secret agency informants. So they were sure that if 4 people talks about something, they would know. That's very good solution. Never ever was any rebel in East Germany. It was in Poland, it was in Hungary, it was in Czechoslovakia, but not there. Very good solution, but very costly. Because your control now takes 1/4 of the population, which leaves from spying on friends. That would be very wasteful in US if we would do that. Because in US, unrest raises very slowly, so it's much better if arrest raises, and it happens occasionally in history, you just put the police force and quell it, and that's it. So the cost is much smaller, but the cost now is 2 parts. One, the police will step into this unrest. The other, damage. Sometimes people lost life in these demonstrations. So this is what's unusual about control. But one solution would be oversteering. When the one solution, Stasi solution, would be good. They did a good solution because Germany was rebelling all the time if there would be not this horrible force. So therefore it was rational, it was optimal in a sense. But it was an unusual system, very force upon Germans. Because, you know, despite Marx being born there, anyway. But that shows this difficult choice. Do you dwell everything all the time, that you can pay a lot of cost? Or you say, okay, we are okay, and something happens, we would react. If you quickly react, the damage from existence of the risk for a short time would be smaller than keeping everybody under the choke all the time. Not speaking about the moral cost and sort of like robbing people of any initiative because they would be afraid. What the government would think if I propose, like, for example, network science. They would close me, lock me.
Yeah, please.
So similar to that, I was curious, at the end you talked about deciding, so whatever the energy level would be, that would be required to keep all of these individual risk factors at their minimal stasis, perhaps would be a good measure of the disruption. But kind of along with that, mightn't you say that the best you can hope for is a certain level of higher risk here, lower risk there? There's some sort of stasis in between that's optimal.
Yes, and that's a very good point. And if the risk is not very damaging, like for example, you can allow some inflation, you can allow some corruption, it's not as, if it's not too much, you know, and so forth. And so forth. So there are things which the cost probably is lower to tolerate it at the tolerating level than trying to extinguish it to the very end. The other thing which is also sort of important when we discuss that is that this energy, of course, as I mentioned, could really, it's like abstract unit, but it really could be translated for each risk into number of policemen hired in social systems, how policemen oriented the country is. Of course, could be like in, you know, law and restrictions on industry and so forth. Maybe supranational control of the weapon of mass destruction, totally destroying them, and so forth and so forth. So some of them are totally unrealistic, but they could be sort of assess how costly it would be or very possible. So sometimes the cost would be infinite. Like, you know, and we are also guilty a little bit of it if you think about it. Ukraine destroyed voluntarily all the weapons of mass destruction they had because they had the treaty signed by Russia, United States, Britain and France. And Russia then attacked Crimea and attacked the boundary with Ukraine, and the other three signatures, okay. So what other powers we have, there's no reason whatsoever for them to give the weapon of mass destruction. If Russia would have a weapon of mass destruction, Russians would be afraid that they would go crazy and attack them. So people learn. So therefore, that's a failure of global, governing, because there are no sanctions on Russia for that. And that shows in this risk. In fact, we were working for DITRA when we started it, and DITRA asked us to run simulation. What is the most influential risk for spread of weapon of mass destruction? Invariably, it was coming out failure of global government, meaning that breakers are not punished. Breakers are not punished. Then, of course, that's the lesson for others. That it's better to have weapon of mass destruction no matter what the price. And no. It's sad reality, unfortunately. So sometimes computers are more objective than we are because we don't want to see these facts. But nobody was saying, okay, now we signed this treaty and we renege on it. None of these three governments, none of them said so.
Okay, on this thoughtful and sad conclusion as well, you know, worrisome at least, you know, thank you again, Bob.